Hi, welcome to the AI code repair presentation. In this presentation, we'll be summarizing the work packages done in this project. So the motivation behind this project is that software costs businesses quite a lot of money, as programmers spend around 2.5 hours trying to locate, reproduce, repair, and test fixes to software vulnerabilities that are discovered. The poor software quality costs US companies around $2.41 trillion in 2022, and the accumulated software technical debt has grown to around $1.52 trillion. So the objective is to combine large language models and formal verification to generate an efficient, robust, and secure AI code. The diagram below summarizes the method of this. At the beginning, we have the source code, which may contain a vulnerability. And if it does, we have the verifier output. We create a prompt. We use the large language model to fix the code, and then we verify it once more and return the result. If the vulnerability has been fixed and the code is now safe, we return the patched source code as well. To elaborate on how we automatically repair AIC code, we use ESBMC as a memory safety verification engine, also known as an oracle, and we use large language models to propose program mutations to fix the AIC code. So the tasks of the AI code repair was to build a large dataset with AI code to demonstrate how this automated approach can repair software vulnerabilities. The second task was to develop an automated counterexample guided framework that ensures that AI systems exhibit safety and security. And the third task was to evaluate the developed ASBMC-AI framework's ability to fix flaws. And we are limiting the scope to memory safety in C and C++ source code. So for work package 1, we grabbed the neurocode bench, which was around 505 samples, and we used program mutations to expand it to 80,000 samples, which contain memory safety vulnerabilities. So the original neurocode bench contained AI safety vulnerabilities, which was used as a benchmarking tool to test software verifiers, and the expanded dataset was limited to just memory safety vulnerabilities. The mutated code produced safe and unsafe code. So for future large language model training, this dataset has unsafe and safe code. Unsafe code can be used to show the LLM problematic examples. In this case, it can be the X train, and safe code can be used to show the large language model how to fix the vulnerable code. In this case, it can be the Y train. The graph shows how many safe, unknown, and unsafe samples each category in the base dataset had after it was expanded. So for work package 2, we used prompt engineering techniques to find the best prompt for AIC code repair, and our findings show that the best prompt was managed to achieve 18% successful repairs, and the best source code format was to use single line, which means to show only the vulnerable line of the source code rather than show the source code in a contextual manner. And we experimented with simple direct prompts and also persona prompts, and we found out that persona prompts worked better than the simple direct prompts. And the best role for the persona was automated code repair tool. We also found that showing the source code after the verifier output showed better performance. We also found that providing raw feedback from a verifier makes the performance worse, so the feedback had to be formatted. The gray box shows what the best prompt is from the work package 2 experiments. For work package 3, we expanded ESBMC-AI to create an iterative AIC code automated program repair solution. We managed to push the successful repairs from 18% to 25% using this approach. So this means that iterative automated program repair is more successful than single-shot automated program repair, as the ESBMC-AI framework uses iterative repairs. The best temperature for automated program repair is 0.0, and we found out the best number of retries is 2. The best way to show the history of repairs to the LLM is using forward history, and that means that the oldest prompt is shown first and the latest prompt is shown last. So the final verdict of these experiments is that iterative automated program repair is better than single attempt automated program repair. So to conclude, in work package 1, we created a large memory safety vulnerability dataset that could be used to train large language models to repair AIC code. In work package 2, we used prompt engineering techniques to find the best prompt for AIC code repair. And in work package 3, we expanded the ESBMC-AI framework to an iterative AIC code APR solution. So for future work, we will continue experimenting with large language models. We will try to fine-tune in the future our own models that can repair code, more specifically perhaps AIC code, and we will also improve and release our dataset of vulnerable code. Lastly, we'll also augment formal verification with testing regarding ESBMC-AI. So we'll use ESBMC and testing frameworks to verify the code. Thank you very much for watching the presentation.